Okay, so this is Calculus Blue Volume 1. So if you have, I'm just going to go over material like recitation style. If you have questions, raise your hand at any time. So, bit of review. So Volume 1, we looked at dot product, cross product, lines and planes and space, and then all about curves, and then matrix properties and row reduction. So don't forget all those like things from the very first few weeks. Okay, so to start off, dot products, just a quick review. Dot product is where you have two vectors, u and v, and they could have multiple terms. And for the dot product, you multiply each term and then add them up together. So here, if you have a vector u and a vector v, the dot product is u1 v1 plus u2 v2, etc. And you can take the length of any vector. The length of any vector is going to be the square root of, you take each component squared and add them up. And something is a unit vector, that means that the length is 1. And so the length can be used in a lot of formulas. Dot product properties, we have commutativity, which means it doesn't matter what order you dot product things in. If you dot product with 0, you get 0. Here we see that the length squared is going to be the dot product. You can also find the angle between two vectors. The angle between two vectors is arc cosine of u dot v at the top, and then you divide by the length. Yep. Put that on the graph. Yep. Okay. Does everyone see good? Okay. So. So those are just some quick things about dot products. Any questions on dot products? Okay, let's do cross products. So this is just super quick review of basic stuff. Cross product, there's multiple ways you can do cross product depending on how you want to remember it. So you can remember it as this formula, or another easier way of doing the cross product is you can write ijk and write each of your vectors horizontally and find the determinant of that. And that determinant will give you the cross product components. You could also write each of these vertically, so like ijk and then vector vector. And we know that's true because the determinant of some matrix is always equal to the determinant of its transverse. So it doesn't matter if you write them horizontally or vertically. And for cross product, we also have some properties here. It's different from dot product in that if you switch the order, a negative sign comes out. If you cross it with 0, you still get 0 though. And also this is a nice property of cross product, which is that if you cross product with itself, you get 0. Okay, so from this, we know that if you do the cross product, so u cross v, that result is always going to be orthogonal to each of the vectors that you cross product with. So u cross v is orthogonal to u, and it's going to be orthogonal to v as well. Now, if you want to see whether two vectors are parallel, then you see that one vector should be a multiple of another vector. That means that they're parallel. Okay, and in other words, if you want to see two vectors are parallel, their cross product should be 0. Okay. Now we have, so we also have the standard basis vectors. Those are I, J, K. How you remember the order is you just draw a like triangle type of thing. So if you do I cross J, you get K. If you do J cross K, you get I, and you keep going in a clockwise rotation. If you go counterclockwise, oh hi, you can just sit on the floor. If you go counterclockwise, negative sign comes out. Okay. If you want to find the area of a parallelogram, that's also turns out to be the cross product, but you take the length of the cross product. Or you can also do the length of u times length of v times sine of theta, where theta is your angle between the two vectors you're choosing. Another thing we have is the scalar triple product. Don't forget that. That's where you have the cross product first, and then you do the dot product. So you can do it the long way, where you actually do the cross product and then dot it with u. Or an easier or a simpler way is you can take the determinant of, you write each of the vectors in a column. So for example, to do the scalar triple product, I could write each of these vectors vertically like this. So W1, W2, W3. And then I take the determinant of that, and that should give me the scalar triple product. We also have some more properties of cross product, which this is all about the ordering that you do these in. So again, it follows the IJK kind of rule where U, V, W. If you go in the clockwise way, these are all equivalent. If you want to switch up the order, a negative sign comes out. So here I have our first example of a triple scalar product. Wait, am I using the right document? Okay. Okay, so for example, if we have U equals this vector, V equals this vector, and W equals this vector, how can we find the scalar triple product? Well, I can write each vector as a column. So 1, 2, -1, -2, 0, 3, 0, 7, -4. How do I do the determinant? Well, I can use minor expansion. So what that is I take my first number, so 1, and I imagine crossing out that row in that column. The remaining matrix, that determinant, is what I should multiply by. So I should multiply by the determinant of 0, 3, 7, -4. And then I have to alternate signs. So I do a minus sign, -2, times, I imagine crossing out that row, that column. What am I left with? I'm left with 2, -1, 7, -4, plus the last number, 0. 0 times anything is 0. So the thing to remember is that they alternate signs. And so I can finish this computation. I get 1, 0 minus 21 plus 2, because minus negative is plus, -8 minus -7. So this gives me -21 minus 2, or -23. Yes. Yes. Oh, yeah, sorry. You can sit on the floor or. Okay, any questions on anything so far? Okay, let's move into equations of lines and planes in space. Okay, so we saw that this was used a lot throughout the entire semester. You always have to know how to write the equation of a line and a plane. So let's start off with a line. For any line, you need some point, and you always need a direction vector. That's kind of like how when you're writing a normal line, you always need like a slope and a y-intercept, except here you need a point and a vector. You might have to move to the front, or yeah, you can go. Sorry. Yeah. Okay, so for any point and direction vector v, the equation of a line is given by r of t equals the original point plus your variable t times your direction vectors. You can also write it, so this is written like implicitly, you can also write it in a component form, meaning you take x and you set it equal to the original x value plus t times the x coordinate of your vector, your direction vector. And y would be the same, z is the same. And this is technically because this r naught, it's a 3×1 vector plus t times the vector also has 3 components. So you can either write it all together or write it by row. So let's do an example. Let's say we want to find the line through this point and parallel to this vector. Then what can I do? I can follow the formula. It says my equation of the line is the original point, so -2, 0, 4, plus the variable I choose is t, and the direction vector they give me is 2, 4, -2. So I can write it that way, or I can say r of t is x equals, I take the first row, which is -2 plus 2t. The second row is 0 plus 4t. And the last row is 4 minus 2t. Yeah, any questions so far? Okay, and we can also write the equation of a plane. So similarly here for a line, we always need a point and a direction vector. For a plane, we also need a point, but now we're gonna need the normal vector. So you always have to find the normal vector. And the equation for that is the normal vector dot with, you need some sort of like direction. So you have, this is gonna be x, y, z, some arbitrary variable, minus your original point, x naught, y naught, z naught. That's all dot producted by whatever your normal vector is. So I'm going to say the x component of your normal vector, y component, and z component equals 0. That's how you write an implicit equation of a plane. And you see that if I simplify this dot product, well, what do I get? I get an x and y and z dot with, this is x minus x naught, y minus y naught, z minus z naught equals 0. And when I do out that dot product, I'm multiplying components. So I have nx times x minus x naught, you see that here, plus ny times y minus y naught, plus nz, z minus z naught. So that's always the equation of your plane. And you always need some normal vector. You can think of it as your slope or like your direction vector. So in general, if you're trying to find the equation of a line, I would say you should use the parameterization formula, meaning like you want to use this version of the formula if you're finding a line. And if you're trying to find a plane, you should always find the implicit equation. So that's the n dot x, y, z minus whatever point you have. So line, parametric, plane, implicit.
Are you gonna post the recording on Canvas?
I'll post on my website. Yeah. Okay. So let's do an example. If you have, how do we find this normal vector? So like sometimes they tell you, oh, the normal vector of this plane is this. But other times if they don't tell you, you have to find it. So how do you find a normal vector? Well, we can take two vectors on our plane. So two non-parallel vectors that live on my plane. Often I find that by like they're the tangent vectors. If I take the cross product, I know from cross products that I just reviewed above that whatever the result is, it's going to be orthogonal to B1 and it's going to be orthogonal to B2. And so that's exactly our normal vector. So if I find two non-parallel vectors on my plane, do the cross product, I have exactly my normal vector. You also know if three vectors are, if their triple scalar product is 0. So we can remember what is the triple scalar product like telling you? Well, how do we calculate it? By doing the determinant vectors. What does the determinant of three vectors do? That's calculating the volume of the parallelepiped spanned by those three vectors. So parallelepiped spanned by three vectors. So if you imagine the volume is 0, that means that your entire thing is flat, like there's no volume at all. So if the triple scalar product is 0, you know all three vectors on the same plane. Okay. Now for any curve, we can also find the arc length element. So that is dl, the arc length element. That's going to be the length of your velocity vector. And so we recall that Grice likes the smiley face notation. So any smiley face is integral d smiley face. So if we wanted to find the actual arc length, you take the integral of the arc length element. So L equals integral dl. Okay, also in this unit, we were talking about like unit tangent vectors, unit normal vectors. Those are where you start off with some position equation given as r of t equals something. You can take the derivative, so that's dr dt, and you divide it by its length. That's going to give you the unit tangent vector. If you then take that tangent vector and take its derivative on the top, divide it by the length of that, then that's the unit normal vector. And these two vectors are going to be orthogonal to each other. And we can think about why that is. It's because say you have some curve, right? And we have some tangent plane. So this purple plane. The tangent vector is always like on your plane. So imagine this red line is your tangent vector that's on my plane. The normal vector is always the one that's sticking out. So the normal vector is going to be like this green one sticking out. And the normal vector is always orthogonal to your tangent vector. Yeah.
What's dr in this case?
Dr dt as a whole is the derivative of r with respect to t.
R is the plane.
R is the equation of like the position equation you're given. So we always like you're given r of t, and then you take the derivative to get v of t, or sometimes we write it as dr dt. And then like the next derivative is like acceleration. Okay. Does anyone want to see? Okay, I'll just do it. Okay, so I have an example question. So for example, here. You're given a parameterized curve. So here they call it gamma. In my notation, I called it r. We can also call it gamma though. And they say to compute the velocity vector. Well, velocity vector is always the derivative. So part A, find the velocity vector of this parameterized curve. That's going to be, I take the derivative, and they say find the velocity vector at t equals 0. So first, let's find velocity vector. I take the derivative with respect to t. Derivative of 4t minus 7 is 4. Derivative of 3 minus sine 2t is negative 2 cosine 2t. Derivative of the third row is negative 4. Derivative of cosine 2t is negative 2 sine 2t. So that's my velocity vector. But if I want to find the velocity vector at t equals 0, I plug in 0. And so I get 4. Cosine of 0 is 1. So I have 1 times negative 2 is negative 2, negative 4, and then 0. Now, if you're asked to compute the tangent, the unit tangent at t equals 0, what is t? T is always the velocity over the length of the velocity. So we have our velocity vector, which is 4, negative 2, negative 4, 0, divided by the length. The length is always the square root of each of the components squared. So I have 4 squared plus negative 2 squared plus negative 4 squared plus 0 squared. So that gives me this vector on the top. 16 plus 4 is 20 plus 8 is, 16 plus 4 is 20 plus 16 is 32. 36, sorry, square root 36. So my final tangent vector is going to be 4 over 6, negative 2 over 6, plus you, negative 4 over 6, 0. As an extra question, what if I wanted to compute the arc length of this curve? Well, the arc length element, well, to compute the arc length, we need the derivative of the arc length element. What is the arc length element? Bless you. That was the length of v dt. I already found the length of V. That was my denominator, 6. We're gonna have integral of 6 dt. My t is going to go from, 0 to pi, because they stated it in the question. So t goes from 0 to pi. So I get 6t from 0 to pi, or 6 pi. Any questions so far? Okay, so let's move on to matrices then. Okay, so matrix properties. So in general, matrix multiplication is not commutative, meaning multiplying a matrix A by a matrix B is not the same as doing B then A. So they are different. So order does matter. There are certain cases where matrix multiplication is commutative though. Those cases are where both your matrices are diagonal. So if A is diagonal here, a diagonal matrix is where you have non-zeros on the diagonal, and B is a diagonal matrix as well, then you can actually do the matrix multiplication both ways and you get the same answer. So AB equals BA here. Note that to be a diagonal matrix, it just means all the non-zeros have to be on the diagonal. So for example, 3, 0, 0, 0. Let me make it a bigger matrix. Let me say 3, 0, 2, 0, 0, 0, 0, 0, 0. Like this is still a diagonal matrix, even though there's a 0 here. Because as long as all my non-zero terms are on the diagonal, it's a diagonal matrix. Yes. No, it has to be, this is the main diagonal. So it has to be top left to bottom right to be called diagonal matrix. No. Okay. So there's another case where it might be commutative, which is if B is a scalar matrix, or I should say scalar multiple of the identity. Scalar multiple. So A could be any random matrix that you want it to be, but B should be a multiple of the identity matrix, which means like the identity matrix, let's recall, is you have ones all along the main diagonal, the zeros everywhere else. So as long as it's the scalar multiple of this, so you could have like 3, 3, 3, 3, 3, or 10, 10, 10, 10, etc., then multiplication will be commutative. And you can test it out by actually doing the multiplication and see we get the same answer. Okay, matrix transposes. Let's recall how to do transposes. You look at your matrix, you take each row and you write it as a column instead. So here I've color coded it. So you have like all the ones in the first row. When I take the transpose, it's like kind of moving it a bit. So I move the ones here. I take the second row and I make it my second column, third row, third column. And sometimes in questions, they say like this vector transpose. That's just because it's harder to type out a thing like on LaTeX vertically. So you would just write 1, 2, 3 transpose. But what it really means is this vector 1, 2, 3. Okay, and determinants, we can take determinants of matrices. For a 2x2 matrix, we can always follow this formula. It's always the main diagonal minus the off diagonal. So main diagonal is top right to bottom left. Off diagonal is the other one. So for a 2x2 matrix, determinant is AD minus BC. If you have a higher dimensional matrix, there's multiple ways you could do the determinant. So one way is this cross way. So if you learn it that way, that's fine. Another way is, so that's where you like take the crosses and you add them up and then you subtract the other ones. Or you often use minor expansion. So for minor expansion, you look at some element and you multiply by the determinant of what's remaining. And what's important to note here is that the signs always alternate. So don't forget the alternating part. And we'll see later that we learned another way to take a determinant, is using row reduction. So sometimes minor expansion is nice, but other times row reduction might be nicer, especially if you have a matrix that's like 5 by 5 or something, or like 10 by 10. Okay, also a nice trick is that if you have, oh wait, I have tricks here, okay. So if you have an upper or lower triangular matrix, the determinant is gonna be you just multiply the diagonal straight. So if it's upper or lower triangular, or even if it's a diagonal matrix, you don't have to do minor expansion, all that stuff. Just multiply the diagonal terms. So here, this determinant of this matrix is going to be 1 times 2 times 3, which is 6. Even in this upper triangular, it's still 6. Okay, and even if you had determinant of, say, 2, 0, 3, 0, 0, 0, 0, 0. This determinant is going to be 2 times 0 times 3, because those are the terms on my diagonal. So it's going to be 0. Okay, and some other properties of determinants. As I said before, determinant of a transpose is equal to the determinant of A. If you wanted to do the determinant of AB, you can separate it and do the determinant of A times the determinant of B. For this case, you sometimes want to be careful though. This only works if A and B are invertible. Then you can use this trick. Otherwise, if A is like a 2 by 3 matrix, for example, and B is a 3 by 2 matrix, then you might say, oh, the determinant of A doesn't exist because it's not square. But by multiplying A and B, you can see that you might be able to do the determinant. So you can't always use this rule unless A and B are both invertible, meaning they're both square. Only square matrices have determinants. Okay, and we also have some more properties. If you wanted to take the determinant of a transpose matrix, you don't have to actually take the, inverse. You don't have to actually take the inverse of the matrix and then take the determinant. You could just do the determinant of A and do 1 over that. And that will be the determinant of your inverse. If you multiply a matrix by some scalar C, that's going to multiply the determinant to the n, where n is like the number of rows you have. And the idea why this is true is we'll see later with row reduction. So if you recall from row reduction, if you multiply a row by a number, it multiplies the determinant by that number. So if you have, say, 3 rows and you multiply each row by some scalar C, then you'll multiply it by C 1 time, C again for the other row, and C a 3rd time. Yeah. So you can, so if A and B are different sizes, then you can't use this trick, this second property, meaning you can't split it up and say determinant of A times determinant of B is determinant of AB. You have to actually multiply these two together first, get AB, and then take the determinant of AB. Yes. As long as once you multiply AB, it's going to be a 2 by 2 matrix. As long as that is invertible, then you can take the determinant. Or as long as it's square, you can take the determinant.
Oh. So the product has to be
Yes. Yes. Okay. Determinants also have other ideas, which is that we can find the area of a parallelogram if we take the determinant of the 2 vectors that the parallelogram is spanned by. And we saw before that the volume of a parallelepiped is the determinant of the 3 vectors written in columns. Okay, we also have block matrices. So block matrices are nice because they also have more tricks, which is that here, this A1, this could be a smaller square matrix. So I could have this be like 2, 3, 4, 5. A2 could be maybe like 1, 2, 3, 4, 5, 6, 7, 8, 9. They can be different sizes as long as they're square. Then if I want to multiply these 2 matrices, I can just multiply each of the separately, pairwise. So like A1 times B1 is my first left-hand corner, then A2 times B2, etc. And same for inverses. Instead of finding the whole inverse of this big matrix, I can take the inverse of each of the smaller square matrices. And that will be the inverse of my entire block matrix. Okay, and also if we wanted to take the determinant of A, for example, instead of doing like a big minor expansion thing, we can do the determinant of the first, the green block, times the determinant of the purple block, times dot dot dot, all the way to the determinant of the nth block.
Sorry, could you just explain like block matrices one more time?
Yeah, so block matrices are where you have these blocks of square matrices on the diagonal only, and everything else is zero. So for example, this matrix here I've written is a block matrix because in this top left corner, I have a square, 2, 3, 4, 5. And here I have this 3 by 3 matrix, but it's still a block. And I would have like other here. And so overall, this matrix A is a block matrix.
So A is a matrix of matrices.
Yes. Of like smaller square matrices.
And it's possible for A to be like not triangular, like not upper triangular, like it could be like.
It has to be diagonal only. So everywhere,
only.
yeah, everywhere else should be zeros.
Oh, okay.
Wait, what would it mean if it's like A1 times B1 if they're two different sizes?
So they have to be the same size. So like B1 here could be like 1, 2, 3, 4. Then in that case, in the top left-hand corner, it would be whatever the multiplication result is. So like 2 plus 9 is 11, whatever this number is in this number.
So to use these properties, the block matrix has to be diagonals.
Yes. So you have to have like some block here, some block here. Think of the blocks as like your diagonal elements.
So it looks like each block has to be the same size.
Mhm.
It has to be the same size in order to do this.
To do multiplication. So like here in my product rule, I said I can just do A1, B1, but I can only do matrix multiplication if the sizes like match up, right? So this green 2 by 2 matrix, if I want to multiply it by B1, then B1 here should also be a 2 by 2 matrix. And
But
here,
it's still considered a block matrix even if A1 and A2 are different sizes.
yes, then you just can't multiply them. Yeah, so like here, if B1 at the top was like 1, 2, 3, 4, 5, 6, 7, 8, 9, A is still a block matrix, B is a block matrix, but you can't multiply them. Like you can't multiply them directly, meaning you can't use this trick.
So if we're doing like two block matrices, we're told to split them into like blocks.
Mhm.
So we need to split them in the same, so that they have the same dimensions for each block.
Only if you want to multiply things.
Only
So like if they gave you some random matrix like 1, 2, 3, 4, like this, and 1, 2, 3, 4, 5, and zeros everywhere else. So 0, 0, 0, 0, like that. Then you can see that the blocks are going to be this block, and this block. So from this, I can take the determinant of A. Determinant of A is going to be determinant of the top block, the 3 by 3 thing, times determinant of the 2 by 2 thing, times 5. If you wanted to take A and multiply it by something else, like this matrix B, then you have to see if the matrices are the same size.
they have to be the same size.
If you want to use this trick to multiply them. Otherwise, you have to actually multiply how you normally multiply.
So each block has to be.
Any other questions on matrices? Yeah. Meaning like if you wanted to multiply A by B, then this left-hand block is a 2, and B top block, it should be 2 by 2. If I want to use this trick and just multiply the blocks to get my left-hand side. a 3x3 matrix like I have here, then I can still multiply these matrices, but I have to do it the long way, which is like take the row, multiply by that. Like how you normally multiply by matrices. Yeah.
Does each block have to be square?
Yes. Okay. So let's talk about row reduction. Okay. So row reduction, this is usually used when we're solving equations like AX equals to B, where A is some matrix, X is maybe some vector like with variables that you're interested in, and B is another vector with numbers. Two methods to solving AX equals to B. First, you can make a big augmented matrix, meaning I write my entire matrix A, and then I write my B vector. And then you do a bunch of row reductions, back substitute, and you get your answer. Second method is you can do the inverse. So you have this matrix A, you could take its inverse, and we see that we can multiply by the inverse of A, both on the left-hand side. And then this simplifies, A inverse A simplifies to the identity matrix. So X equals A inverse B. And so that would give you your answer. Note that this method only works if, first of all, A is invertible so that you can find A inverse. Also, even if it doesn't have an inverse, it doesn't mean that there's no solution. You could have infinitely many solutions. So if A inverse does not exist, it only means you can only assume that there is like you don't have exactly one solution. You could have no solutions or you could have infinitely many solutions.
Wait, back substitution is when you like add the rows together?
Okay, yeah, so back substitution is where you do row reduction. So you might get like, let me say 1, 1. Let me make this a nice example. 2, 3, 4. So say you've done your row reduction and you got to this point. Then what you do is you look at your last row.
Oh,
Yeah, and this is like Z equals 2. This is like Y equals 3, X equals 4. Okay. Yeah.
how do you determine it has no solution or good solution?
Then you have to do row reduction. And so, yeah, I'll have more pages on that. So if you can't find an inverse, that doesn't always mean there's no solution. That just means you should try row reduction instead. Okay, so yeah, a couple of notes is that if the determinant of your matrix is 0, remember the inverse doesn't exist. And yeah, if it's not 0, then you should have a unique solution. Okay, so how do we do row reduction? So we start with some complicated matrix A. We do a bunch of steps, row reduction, and we get to a reduced matrix. The goal of row reduction is that we get to this nicer matrix, which is probably upper triangular or lower triangular or diagonal. And we know that those matrices are easier to find the determinant of because you multiply the diagonal terms and you get the determinant. Upper, lower, or diagonal. And how do you get, so you have this nicer matrix, you take the determinant, and that's determinant of R. But I did all those like row reductions, and so I have to account for that. So to get back to my original matrix A, the determinant of that, I have to divide by everything that I just did, all the row reductions I did. So when you change or switch 2 rows, that multiplies the determinant by -1. So in order to get back to the original matrix, I would take my reduced determinant R and divide by -1. Scaling a row multiplies the determinant by that constant. So if I want to go backwards, I divide by that constant. And combining rows doesn't do any change to the determinant. Now, note that when you're doing combining, you want to make sure that So here I have like row 1. I'm gonna do row 1 is row 1 plus 2 times row 2, for example. And this determinant has no change. And that's what you want to be careful when you're doing combining, because these two numbers here, they should stay the same. If I said like row 1 is 2 times row 1 plus 2 row 2, that's not a combination anymore. That's first a rescaling because I changed the R1 term, and then I did a combining next. So this is not same as combining. It's only combining if you keep your original row the same and you make any changes extra.
The root scale, is it times, like in this case, would it be times 2 or times 1
Times 2. So what happens is you have some determinant A. So say this determinant is like 2. I do a bunch of row reduction. So I did a rescaling. And then I got my final answer has a determinant of 100. In order, yeah.
We won't actually know the determinant of theta, right? So our final.
Oh, yeah, sorry.
determinant will be, like divided by 2.
Yes, you're right. So like you have this complicated matrix, do a bunch of, say I did a single rescaling and I got this final determinant has a matrix has a determinant of 100. Then to get back to my original matrix, I do 100 divided by 2. Say I rescaled by 2. So the determinant of my original A, this is A, this is R. Determinant of my original matrix A will be 50.
to get back to?
Yes, but I would think of it as dividing by 2 so you don't get confused.
It's like if like to row reduce it, if you
Mhm.
multiply a row by a half,
Yeah.
then you would multiply your other thing by half as well, or by 2.
Yeah.
Yeah, okay.
So like whatever you like doing any operation multiplies your determinant. So you get to this row reduced matrix, but you want to go backwards. So you do like the opposite operation. So you divide by whatever happened. Okay. Does that make sense to everyone? Okay, so we can also find inverses, right? So for an inverse, if you have a 2 by 2 matrix, you can always follow a formula, and that's always going to be 1 over the determinant times, here you switch the main diagonal terms, and then you take the negative of the off diagonal terms, and that will be your inverse. And a rule for inverses is that if you take A and multiply it by its inverse, you should always get the identity matrix. And that's good for us because the fact that you can multiply A times its inverse, giving you identity, that means we can use row reduction if you have a bigger matrix. So for higher dimensions, in order to get the inverse, what I do is write a big augmented matrix. I write A on the left-hand side, and then I write the identity on the right-hand side. I do however many row reductions I need until I get the identity on the left-hand side. And then whatever's on the right-hand side, that will be my answer. That will be the inverse matrix. Okay. So that was some row reduction. Any questions so far? Yeah.
I feel like when you, that's true because when you do the reductions, your inverse is like coding back to the inverse.
Yeah. Okay, so let's do linear transformations. Okay, so linear transformations, we recall that the identity matrix, what does the identity matrix do to a vector? It doesn't change anything. So the identity matrix represents a linear transformation of no change. So the thing we want to remember is any matrix represents a linear transformation. So anytime you're multiplying by a matrix, you're doing some transformation. Okay, and what are the 4 main types of transformations we have? We have rescaling, projection, shearing, and rotation. So first one, rescaling. Rescaling is where you can stretch or shrink the x-axis, stretch or shrink the y-axis. And so how do you figure out like what a matrix does? Well, we look at this first column. The first column represents whatever happens to your I vector. In other words, what happens to your I vector 1, 0? Well, here my matrix says it's 2, 0, which means that I multiplied my I vector by 2. In other words, I stretched the x, I stretched horizontally by 2. Then I look at my second column and I see what it does, what it did to the j vector 0, 1. Well, it multiplied it by -0.5. -0.5 means it compressed vertically, because this is the j vector we're talking about. Compressed vertically by 2 because it's a half. And then there's a negative sign, so it flipped it also. Yeah.
Flip them on the x-axis.
Yes. So here I have a picture, right? We look at our I vector, our j vector. What happened to the I vector is the first column. It multiplied it by 2. So I can draw it like this is my new green vector. My orange vector, it shrinked it by 2. So I can imagine a tinier, let me draw a dotted line here. But when it flipped it, so my actual j vector is this solid orange line. Okay, then I have projection. So you can project vertically onto a line or project horizontally onto a line. So, okay, so here I've written kind of formulas. I wouldn't recommend memorizing them. I just put them there so you can see it. Generally, what you should do for projections is see what happens to the I vector, and you write that as your first column. What happens to the j vector, and write that as your second column. So for example, here, let's say I have my original I and j vectors, and I want to project it to some line, some ax plus by equals 0 line. If I project it vertically, what do I do? Well, this green vector, it goes down because I'm projecting vertically. It goes down to whatever this orange or dot is. And that pink dot ends up to be the point 1 negative a over b. The reason or how I can find it is that I'm projecting vertically. So whatever point this pink dot is, it should have an x value of 1 still, because it's still on the same like x line. So I should plug in 1 to my line, and I can solve for y, and I get negative a over b. So in my first column, I write 1 negative a over b. What happens to the orange vector or the j vector? I project it vertically down and it goes to the origin. So I write 0, 0. And I can generalize this to any line I choose. The reason I have 2 different ones is that, like, as always, a formula specifically doesn't always work super well. So that's why I don't recommend just memorizing these. Just remember what happens to the I vector, what happens to the j vector.
If the line doesn't cross the origin, j vector will not be projected onto.
Yeah. So then that would be a different, like, you can't use this formula. You should actually look at what happens. But generally, they should go through the origin. Okay, and you can project horizontally, which is the same idea. You want to see what happens to your I vector, what happens to your j vector. Okay, we also have shearing. So 2 directions again. You can shear along the x-axis, and you take the y-axis to some line. Or you can shear along the y-axis and take the x-axis to a line. So here, for example, if I wanted to shear to this purple line, what happens? So this is shearing along the x-axis, means I keep my x-axis the same. So my I vector is still 1, 0, no change. The only thing I change now is the y vector. So sorry, I keep saying, did I say a lot? Okay, j vector. This j vector, I want to move it to the purple line. So you see that it becomes this, it moves to the purple line. And how do I get that vector? Well, it should have a y value of 1 because C has the same y value. And then I just have to find the x value. And the way I find the x value is I plug y equals 1 into my equation and solve for x. So for projecting, you're always changing two variables, both like columns. Yeah, you're always changing both columns. Whereas for shearing, you see that you keep one column the same, change the other one. So that's the difference between shearing and projecting. And as I said, you could also shear along the y-axis, meaning you keep the second column the same, change the first column. Okay, and then you have rotations. I would recommend just memorizing this. The rotation matrix is cosine, sine, negative sine, cosine. And that's always for counterclockwise. So if it asks you for the rotation 30 degrees counterclockwise, you plug in theta equals 30 degrees. But if they said 30 degrees clockwise, then you plug in negative 30. So if they say clockwise, just do the negative. Okay. Any questions so far?
Could they ask like two separate components of the rotation, like rotate the I and J components by different angles?
They could say they have, for example, they give you a 3x3 matrix, and they could say what happens in like the YZ plane. Then for that, you want to look at all the terms in the Y and Z components. And then that's now a 2x2 matrix, and maybe that's a rotation in the YZ plane. Like if it was cosine of 0 is 1, 0, like for example that, and they ask you what happens in the YZ plane, you see that we get this matrix if we plug in theta equals 0. Or I should have made it a better example, like 5/2, so 0, 1, negative 1, 0. Then we would say it's rotation 90 degrees counterclockwise in the YZ plane. Okay. So I just put some nice common things like reflection across the y equals x plane is this matrix often. Those are some things. Yeah. Okay, so for example, if you're given this matrix and they said, what happens to the z-axis? Then what would I look at? So I have consider some transformation. Any matrix is a linear transformation from whatever number of terms this is. This is 3 columns by 3 rows. So it's R3 to R3. What happens to the z-axis? For that, I look at what is the number in the third position? Meaning this is like our z column, this is like our z row. What does this -2 say? It says we're going to rescale the z-axis by a factor of 2 because there's a 2 there, and there's a negative, so it's going to reflect across the xy plane. Let's see. Okay, so let's look at this example. So we have this linear transformation, A, and they decomposed it for us into 3 smaller matrices. And they say, what does A do? So we want to remember that wrong question. Let's look at this one. Okay, so the unit disk gets sent by applying A to some region whose area is what? Well, you always start off with some area. So say this is A, and you have determinant, let me call it R. Let me call it B, determinant B. We do a bunch of matrix multiplication. So this matrix A, some linear transformation. And we want to see what is the resulting area. What is this area? Well, by doing this matrix transformation, I'm multiplying the area of my parallelogram by whatever the determinant of this transformation is. So in other words, let me call this R, area of R. Area of R is going to be area of my first shape B times the determinant of A. So in order to get the area of my new shape, I take the area of my original shape, which is the determinant of B, times the determinant of whatever my transformation is. How can I get the determinant of A? I don't want to actually multiply all three of these matrices because that's a lot of work. Instead, I can take the determinant of each one separately and multiply them. So the determinant of the first one is 1. Determinant of the second matrix is 0 minus -1, still 1. Determinant of the last matrix is 3/2. So determinant of A in total is 1 times 1 times 3/2 or 3/2. What is the area of my, so I have times 3/2 here. Now I need to see what is the area of B, my original shape. My original shape, they say it's a unit disk, which means it's a circle of radius 1. Area of a circle is pi r squared, so we get pi times 1 squared or pi. So my final answer is 3/2 pi. That's what A does to my unit disk.
Would you be able to solve this problem if you looked at how each of the three matrices like rescale the x and y?
That would be like them asking like, what does A exactly do? Like what the linear transformations exactly do. Then you look at each one separately. But because they're asking for like the actual area, you need a number. And so the way to do that is you should use the determinant, because just knowing that it's like rescaling something doesn't tell you too much. Like it's just telling you what happens to like axes separately, but you want to know what happens in total. Okay, let's move on to change of basis. So recall that a basis is orthogonal if the basis vectors are mutually orthogonal, meaning you take your matrix, you look at each of the vectors, and each of the dot products should always be 0. That's what it means to be orthogonal. Then further, if each of the vectors have unit length, then your basis is orthonormal. Okay, so I put an example there, but let me move on a little bit. So for example, say they gave you this basis, 1, 2, 1, 1. I want to rewrite the vector 1, 2 in terms of this basis. Then how do I do it? Well, I write it as a linear combination of the basis vectors, meaning 1, 2, I want to write as something times the first basis vector plus something times the second basis vector. And whatever these two question marks are will give me 1, 2 in this new basis, new like different basis. So we can see a little bit that, well, if we just multiply 1 by the orange vector and 0 by the green vector, we get exactly 1, 2. So in this weird B basis, 1, 2 is actually 1, 0. We usually think of 1, 2 as just in the standard basis, like using I is 1, 0 and J as 0, 1, which is why usually in the standard basis, we just say it's 1, 2 but what we're really implying is that it's in the standard basis, 1 times the I vector plus 1 times the J vector. Okay, and yeah. What if in general you wanted to find, okay. Say in general you're given some basis, has lots of vectors in it. I want to rewrite this vector in terms of that basis. Well, then how do I do that? So I have like my new vector, right? And I said that I want to write it as a linear combination of the basis vectors, meaning it should be something times u1 plus something times u2 plus something, a bunch of somethings times their u numbers. Like that's what I want to do. And I want to figure out what these question marks are. Is there another way to rewrite this? Well, there is, because we can rewrite this as this is 1 u2 un all multiplied by, let's say these question marks are x1 x2 xn, x1 x2 xn. And this works because another way of doing matrix multiplication is like you take this x1, you put it in front of the first column. You take this x2, you put it in front of the second column, etc. So we can rewrite this almost dot product as this matrix times x1 to xn. And now this should look familiar because this is ax equals b. So a change of basis problem is essentially solving ax equals to b. Okay. Yeah.
There, where is 1 to s should be 1 times 1 0 plus 2.
Yes. Sorry. Yep. So in the standard basis, 1 times the I vector plus 2 times the j vector is 1, 2. Okay, let's do a example. Okay, so here we want to have, they give you this x. And you want to rewrite it in terms of the new basis where you have u and v as your new basis. Then what do you do? Well, I want to write what is x. X, I'm going to write it as a vector, so it's nicer to write. It's 10, -3. U is 2, -4. And v is 2, 1. So to get my new basis, I want to say 10 -3 equals some number. I want to find out what this number is. Times 2, -4 plus some number times 2, 1. Let me call these question marks, let me give them names. So I have C1 and C2. This means I'm solving 2, -4, 2, 1 times C1, C2. It equals 10, -3. So I just wrote the 10, -3 on the other side. How do I solve that? I could either row reduce, or because this is a nice small 2 by 2 matrix, I can take the inverse. So C1, C2 is going to be the inverse times 10, -3. What is the inverse? It's 1 over the determinant. The determinant is 2 minus -8. I switch the main diagonal and I take the negative of the off diagonal times 10, -3. And so this gives me 1 over 10. When I do matrix multiplication, 10 plus 6 is 16. 40 minus 6 is 34. And so these are going to be my question marks, my C1 and my C2. Yeah.
So C1 and C2 are, it's like the new vector vision, new basis.
Yes. So I would say 10, -3 in this weird basis, let me call it B. This new basis is written as 16/10 and 34/10. Any questions on unit 1 or volume 1? Okay, let me move on to volume 2 then. Okay, so volume 2. So this is our table of contents. Let's start with partial derivatives. So partial derivative means you take the derivative with respect to one of the variables. Right, and they should generally tell you what your input variables are so that you know how many partials you have. Okay. Would I like to see an example of partial derivatives, or we can skip? Okay, let's look at the derivative matrix. So what is the derivative matrix? Also called the Jacobian. That's where you take the partials, like each of your terms are partials. So each of your rows think of as outputs, and each of your columns think of as inputs. So for the first row, you look at your first output, and you take the partial with respect to each of your input variables. And you keep doing that for the entire matrix. Okay, and that's also written as capital DF. What is the main point of doing that derivative or that Jacobian matrix? It's that we want to do rates of change and look at sensitivities. So when we were doing like matrix multiplication, we would take some matrix A, multiply it by some vector, and we get like some answer. Meaning like, what did the linear transformation do to that original vector is your final answer. For this derivative matrix, you now have a lot of different inputs and a lot of different outputs. And so we want to think of it more as rates of change. So the rates of change of each of your outputs is going to equal, you take the derivative matrix times all the rates of change of inputs at some point A. Okay, and so usually you have like some derivative matrix. X is going to be, they say like the rate of change of the first input is 1, rate of change of second input is 2, etc. And your answer is going to be, this is the rate of change of your first output, rate of change of your second output, etc. And with this, they can ask questions of sensitivity. So like, which output is most sensitive to which input? And they could say, like, which output is most sensitive to changes in inputs. So let's do an example to see how this works for sensitivities. So let's do, So we want to consider a function whose derivative is the following. They say that at the point 2, -1, our rates of change of inputs are Cx, Cy, they don't tell us. And the first output is changing at -4, second output is changing at 1. We want to find what are the rates of change of inputs. Okay, so we have the rates of change of, the derivative matrix. At my specific point, they tell me, my point they tell me is 2, -1. I want to find the rates of change of inputs, Cx, Cy. And they tell me the rates of change of outputs. Well, the first output, they say it's -4. Second output, they say is 1. So I get this question. So what is this derivative? If I plug in my points, I get the matrix is -4, 1/4, 4, 1/2 times equal -4, 1. Now I could, how do I solve this? This is an Ax = b problem. So I could either take the inverse or I could do row reduction. Let me do a row reduction to change things up. So I make a big augmented matrix. So -4, 1/4, 4, 1/2. And I write my ending vector here. And if I row reduce, I'll get my answer. So let's do, I could take row 1 is usually the trick or the common thing to do row reduction is I want to get 1 in this top left-hand corner. And then everything should be nicer. So let me multiply by a 4th R1. So I get -1, 1, -1. I can multiply the second row by, let's say I want to get rid of this 1/4 and make it 1. So I multiply by 4. And I get this matrix. Now I can do row 2 is row 2 plus row 1. Because I want to get this to like an upper, like a diagonal matrix. So I want to get rid of this 1. So if I add the 2 rows, let me keep row 1 the same, but row 2 is I add row 1. So I get 0, 3, 3. I could stop there and do back substitution, or I can keep going and get a straight diagonal matrix so that I don't have to do back substitution. So if I do row 1 is row 1 minus row 2, what? Oh wait, let me first take let me do a third of row 2 so that I get rid of that 3 because I don't like bigger numbers. So 1, 1. Now I can do row 1 is row 1 minus row 2. So I get -1, 0. That's nice. -2, 0, 1, 1. And finally, this is, you don't have to do this, but I'm going to multiply row 1 by -1 so that I get a +1 in that corner. This means that I can now directly read off my answers. C2 or CY is 1 and CX is 2. So my rates of change of inputs were 2, 1. Okay. Okay, so let's see. Using the same derivative matrix, here's another question. Say they said the first output is not changing. That means that, let's take my derivative matrix. It's the same matrix here. And they say my first output is not changing, meaning my first output should be 0 because there's no change. And I'm multiplying it by like CX, CY. What can I say about the rates of change of inputs? Just knowing this. Well, yeah.
CX is like gonna change a lot faster.
Close, almost. Yeah, it's gonna end up being the same, but how do I figure that out? Well, let's look at just like normal matrix multiplication, right? If I do matrix multiplication, my first row is gonna be -4 CX plus 4 CY, and something I don't care about. And we're saying that the first thing is 0. Then I can exactly read off the rows. I have 0 equals -4 CX plus 4 CY. Simplify by adding 4 CX on both sides. Divide by 4. So I get that CX has to equal CY. So the rates of change are going to be the same. Okay, any questions on these? Oh yeah,
So in other cases where it's zero, then we can still
solve it.
solve it and see like the ratio.
Yes. Yep. It's only because this question has 0 that they like you can do this nice thing. Okay. Okay, so then I wrote some differentiation rules. So let me just quickly mention that we have 0 matrix, which you should know, identity matrix. Yes, Ellen, you have like all the sum rules. So like the derivative of 2 functions added together, you can take the derivative of one function and add it to the derivative of the other function. Constant multiple. And also a weird or a nice formula is that if your function can be written as x transpose ax, then the derivative is going to be using this formula. And your matrix has to be squared to do this. Okay, so just following from that, we have one of our more advanced formulas or like differentiation theorems is the chain rule, and then we'll do the inverse function theorem. Okay, so chain rule. To find the derivative of this composition, what do? It's going to be the derivative of f times the derivative of g. But if you're finding this derivative at a specific point, here is where it's important to remember what your inputs are. The input to df should be g of a, not like your point A. And the input to dg should be a. So this is important. This has to be g of a, and this has to be a whenever you're doing chain rule. Okay. And so sometimes things get slightly complicated. So if you're trying to find like a partial, maybe it has like one variable. So for example, w is a function of x and y. So w is some function of x and y. And then they say each of x and y are also functions of t. Then what is the partial of w with respect to t? One way to do it is draw this diagram as I just drew, where you see w, and I saw what is w a function of, x and y. What is x and y a function of? They're both functions of t. And so I get this branch diagram. Each of these lines represent partials. So like partial w with respect to x with respect to t is here. And so what I do is I follow what are the ways to get from w to t. There's two ways. First way is this way. So I multiply those partials and I get this term. The other way is I can go this path. And so I multiply those partials together and I get this thing. And so partial of w, or the derivative of w with respect to t in whole is going to be, you have to add these two separate things. So that is using this like branch diagram rule. Yeah. Okay, there could be harder examples. For example, you want to find w, the derivative of w with respect to t. How could I do this? Well, w has x, y, and z. So let me say w has x, y, and z. They give me what x, y, and z are. X is some function of t. So I can write a t here. Turns out that y is also a function of t. I can write another line. And z is also a function of t. And so I can get that the derivative of w with respect to t is going to be so my first path is the green path, w with respect to x, x with respect to t. I added to this orange path. I won't write it out because it's long, and the red path. Okay. Any questions about the branch way? Okay, so let me do an example. They give you w is x squared plus y squared. X is r minus s. Y is r plus s. I want to find partial of w with respect to r and partial of w with respect to s. So we could do it two ways. First, I can use the branch diagram, which is the classical chain rule. So method 1. I do my branch. So I have w. W is a function of x and y. X and y are each functions of r. But they're also each functions of s. So I have to make a separate diagram for that. Each functions of s. And so partial of w with respect to r is going to be, it's going to be this term. So w with respect to x, x with respect to r. plus this path, the orange path. So W with respect to Y, Y with respect to R. And you would do the same thing for W with respect to S. It should equal something plus something. Method 2, which is often maybe might be faster, is using the chain rule. So the derivative of f of g, it turns out that your terms in the derivative are going to be exactly, well, what is your output, right? Your output is w. Your two inputs are r and s. How do we make a derivative matrix? We take the output as a row. So I'm going to have partial of w's on the top. And each column is an input. So this is going to be r. This is going to be s. So if I just do the chain rule, I'm going to get exactly the partials that I want. Because that is what d of f of g means. So how do we do this using the chain rule? Chain rule. This derivative matrix is df times dg by the chain rule. What is df? So let me write it in terms of partials, right? So what is f? F is like our outermost function. So f is going to be kind of like w is our output, x and y are inputs. So I'm going to have w with respect to two inputs, x and y. G is like our inner function. Our inner functions were like, what's the second layer? The second layer were the x and y's. So my outputs are x's and y's. What are my inputs of those? R and S. So I have R here as the first column and S as the second column. And you see that if I do this matrix multiplication, I have partial WX times XR. That's exactly this first blue term. Then I have partial W with respect to Y times YR. That's exactly the second term. Like if I were doing matrix multiplication. So that's why the first term will be W with respect to R. And if I did the other matrix multiplication, I would get W with respect to S. Exactly. Okay, and so you can work this out with the actual variables, but I just wanted to give a overview. Okay, any questions on chain rule? Okay, let's do inverse function theorem. Okay. So the idea with inverse function theorem is that you have a function f. Instead of finding its inverse and then taking its derivative, which might be a lot of work, we can instead take the derivative of f first. And then because inverses of matrices are like, we have a systematic way of doing it, then we can take the inverse of that matrix. So the right-hand side is usually faster. And how do we find it? Well, oh, I guess here, this is a specific case where we're trying to find it at a certain point A. So it turns out that here, again, these inputs are very important. On the right-hand side, this df should be evaluated at A, but the left-hand side, this should be evaluated at f of A. And that's just the formula that you follow. Okay, so we can do an example. So say you have a function, they usually write it in this format. So be familiar with this format. This is where these are your inputs, U, V, W. And over here, you see like a random S and T, but these are like your labels for your outputs. And they would say like, this is maybe like, I don't know, 2U plus B or something, B squared plus 3W, something like that. And then they give you a function G, which here they're telling you the inputs are X and Y, your outputs are A, B, C. So what are the input and output variables of f of g? Well, for compositions, I always start at the right function, so g. G takes in x and y, and what does it do? It gives me three things, a, b, c, or I'll just say three terms, dot, dot, dot. Then what does f do? F takes those three things, just different labeling, like they're just three things, u, v, and w, and it outputs two things, s and t. So there are two inputs, x and y, for our composition, and two outputs, s and t, for our composition. Okay. What if d of, so we're given that df is this matrix and dg is this matrix. We want to see, is the composition f of g invertible locally where all inputs are equal to 2? So we want to see, like, how do we know if a composition is invertible? We can take the derivative matrix and see if that matrix is invertible. So I want to find d of f of g at my point A. What did the chain rule say? Chain rule said I do df at g of A times dg at A. They gave me df. It's 0, 0, 6, 0, 0, 0. They also give me dg. So I can copy dg. I do this matrix multiplication and I get 24, negative 24, 0, 0. Yes. And note that the reason I could just take the matrices they gave me is because g at A, where A is 2, 2, is still 2, 2. So that's why these inputs are both 2, 2s. Now, is this matrix invertible? Well, its determinant is 0. So by the inverse function theorem, note that the inverse function theorem only tells you that if it's non-zero, if it's not 0, then it's invertible. But if it is 0, it's just inconclusive. So by inverse function theorem, f of g is not necessarily invertible. We don't know because we got the determinant is 0.
Can I ask, why does the derivative being invertible in the functions?
Yeah, so that goes to what the inverse function theorem says. So if I found that the derivative of the composition is invertible, that means I can get this inequality. And that means that this inverse does exist, meaning that f of g inverse does exist. So it's like, if I just deal with f, for example, and I get that df is invertible, that means that this f inverse must have existed. So that's why, yeah. Okay. Any other questions on that? Yeah.
So we're saying that because it's the term is 0 is not invertible.
Yes, because the inverse function theorem only says that if it's not 0, it's definitely invertible. It doesn't say anything about it not being invertible. Okay. So the idea of that, so like if, for example, we got that this was invertible, then the inverse function theorem would say that it's equal to d of f of g inverse, which would mean that we could have found this thing. So the original function would be invertible if this was invertible.
why is the left hand side, why did you call it that?
So that's just the formula, just follow it. It has to do with also chain rule a little bit. So like, yeah, so like d of let me see if I f inverse, for example, at A, by the chain rule, it's df at f of A times df. So I got the order a little bit next. Let me do f inverse of f. So f inverse equals df at A, and that equals the identity matrix because they're invertible. So that means that df inverse at f of A equals df A inverse. That's by the chain rule. So this is chain rule. Okay. All right, let's move on to gradients. Okay, so you can only take a gradient if you have one output. If you have multiple outputs, then you should use the derivative matrix, not the gradient. So what does the gradient have? Well, with the derivative matrix, we had those like rates of change stuff, right? So we had df times the rate of change of inputs equals rate of change of outputs. For gradients, we have something similar in that if we take the gradient and dot it with some direction vector, then we get the directional derivative. So this is for the specific case where, this is for U is units. Then we get something called the directional derivative. But in the general sense, we didn't really go over that too much. So let me write the general sense that we have. In general, the relationship between vector language and the gradient is that we can always do the gradient dot some rate of change vector, rate of change of inputs, and we can still get out a rate of change of outputs. So it's essentially the same thing, but instead of a derivative matrix, we have a gradient instead. So we can always do this. Okay, so okay. Any questions so far? Okay, that's kind of all I had to say about gradients. So let me move on to level sets. So what is important about level sets? For level sets, it's important to look at how many inputs you have. So for example, if you have a function with 2 inputs, that means that your level curve is going to be in 2D. If you have a function with 3 inputs, your level set is going to be called a level surface. And the number of inputs you have does matter a lot. In other words, the dimension of your domain, because your inputs are your domain, does matter. So we can see why that is true. Yes, okay. So for example here, I have this function with 2 inputs. It's x squared plus y squared. If I graph this in like GeoGebra or something, I get this paraboloid shape. What is its level sets? How do I get a level set? I take my function x squared plus y squared, and I set it equal to some constant c. And I can vary this constant. So if c is like 1, what is that equation? It's a circle with radius 1. If c is 4, then it's a circle of radius 2, and we keep going. So the level sets here are these 2D circles. But say we had a function, same function, but they tell us we have 3 inputs, x, y, and z. Now, that means we're in 3D. So if you graph this picture, we can't really graph it because the picture is going to be in 4D. So your graph or your picture is always 1 dimension above however many inputs you have. How do I get the level curve, or sorry, level set? I take my function x squared plus y squared, and I set it equal to some constant c. Right, so if I set it equal to 4, for example, how do I draw that? Now, remember, we're in 3D now. So I have an x, y, and z. If I have x squared plus y squared is 4, that means that I have some circle at, yeah, I have some circle in the xy plane of radius 2 if z is 0. But from this equation, they don't specify what z has to be. Z could be anything it wants to be. Z could be 0, could be 5, z could be -5, it could be anything. And so in 3D, because we have 3 inputs, this function is going to have a level set that's actually a cylinder, not just circles. And so we see that with the same equation, x squared plus y squared, we got yeah, and so like for different c, for example, then you get a bigger cylinder. And so all the level surfaces are cylinders of different radii. Okay, and what's important to note, why did we learn level sets? Remember, level sets are orthogonal to their gradients. So at any point A, the gradient is always orthogonal to the level set. That's going to be helpful for us, because if we wanted to find the equation of a plane, for example, what did we always need? We always needed like the normal vector. So if you have some level set, the gradient is exactly going to be that normal vector because it's orthogonal to the gradient is orthogonal to the level set. Okay. Any questions on that? Okay, let's go into tangent spaces. So we have these tangent spaces, 2 level sets now. So kind of like the equation of planes, but they're tangent spaces. So it's similar to an equation of a plane. For a plane, we had, what did we have? We have the normal vector times like x minus some point, y minus a point, z minus a point equals 0. Now for tangent spaces, instead of this normal vector, we have a gradient. And we're still going to dot it by all those like variable minus original point stuff and set it equal to 0. That's the implicit equation for a tangent space. So here I have an example. Say we wanted to find the implicit equation for a tangent plane at this point to some paraboloid. First, let's see what the level sets are. Right, so the level sets, what do? I take my function. Usually we want to write everything on one side. In this case, it doesn't really matter because when you take the derivative of 9, you still get 0 anyway, but we can move it over just in case. So the level set is going to be level set f of, we have 3 variables, so we're in 3D, x, y, z. It equals, I'm going to write that blue equation. What is this blue equation? It lives in R3, so like 3 dimensions. I want to find the equation of a tangent plane. What do I need? I need the gradient. So let me find the gradient. How do I find the gradient? I take my function. So this is my original function. Yeah, I'll just use the level set function. And I take the derivative. So partial with respect to x is 2x. Partial with respect to y is 2y. Partial with respect to z is 1. And I'm told that I want to find at this specific point. So let me evaluate it at 1, 2, 4. That gives me 2, 4, 1. Okay, and now I just follow my equation. What did my equation say? I have my gradient, 2, 4, 1, dot with, this is all the variables, minus their original points. That's what this x minus a thing means. So I have x minus what original x 0.1. Let me write it. Okay. Y minus what's the original y point? It's 2. And z minus the original z point, which is 4, equals 0. What does a dot product do? Multiplies each component, adds them together. So I have 2 times x minus 1 plus 4 times y minus 2 plus 1 times z minus 4 equals 0. If I rewrite this, I get 2x plus 4y plus z equals 14. So this is our tangent plane in R3.
Could you, I make it, because like, probably given is a level set for level surface, right?
Um,
The level set. You have to move over the line, but you have to use the left side of the.
Usually you want to move it over. Most cases it doesn't matter because you see the derivative of 9 is 0, so it's not used anywhere. So you could have just started with this, the original equation. Okay, so this was writing a tangent space using an implicit equation. You can also write one using a parametric equation, and that's a similar idea to how we wrote an equation of a line. Right, for the equation of a line, we said r of t equals the original point plus t times the direction vector. Here we have a similar idea, except instead of these direction vectors, we're going to have all like the partials with respect to one of the variables. And we're still plugging in like our original point. So for example, yeah, let's do this. I think this is an important example. Okay, we want to find the parametric equation for a tangent plane at this point to this surface given by this. Okay, first I need, what does my formula say? I want my position at some original point. My original point is 192. However, when I'm finding the derivatives, like the derivative matrix of this, for example, like my direction vectors, they're going to have a bunch of expressions in them. I need to know what to plug in to get actual numbers in my derivative matrix. And in other words, I need to find what is T1 and what is T2. How do I find T1 and T2? I set this entire thing equal to 192. And I solve for T1 and T2. So for this example, it's a nicer example, so you can kind of guess a little bit what T1 and T2 might be. So I see I need the first row to be a 1. My first guess is, what if T1 is 1? And let's see if it works out. If T1 is 1, then here I should get, according to this second row, I get 3 times T2 is 9, which means T2 is 3. But we plug this back into our first row, and what do we get? We get 1 minus 6. That's not 1. So we know that this is not the solution. Let me guess another thing. What about T1 is 3 instead this time? Then how do I get the first row to equal 1? I need 3 minus 2 times something equals 1. Well, what if T2 is 1? Then I get 3 minus 2 is 1. That's great. 3 times 1 is 9. Yes, and this last one also works. So this is my T1 and T2.
How did you know it was either 1 or 3 or 3?
I just guessed numbers.
Just
Yeah, like they might make a, if you had to find T1 and 2, they would probably make it nicer. I just had this example here. So yeah. Okay, so we need our derivatives, right? So let's find dr dt. Or sorry, dr matrix. What is dr? It's going to be the partial with respect to t1 and the partial with respect to t2. So what do I get? I have 1, 3, t2, negative 2, t1. Partials with respect to t2 are negative 2, 3, t1, and 1. And you see that these are all like expressions, right? We want like actual numbers. And so I need to plug in the t1 and t2 that I just found, 3, 1. So that means my derivative matrix is 1, 3, negative 6, negative 2, 9, 1. So what's the like formula that I follow? Let me copy and paste. So we have right now this formula saying S is like however many variables you have. We have 2 variables, right? So I'm going to say R of T1, T2 equals my original value, the position at my original point. They gave me is 192. So I have 192 plus, I'm going to take the row, my first column of my derivative matrix. That's going to be the partial of R with respect to, oh, I already wrote it. Yeah, T1. So because that's the column associated to T1, I'm going to say it's plus T1 times that first column, plus T2 times the second column. We can do this because the columns in our derivative matrix, they represent your tangent vectors on your plane. And so we're going to just take those columns and yeah, those are like our directions. Yeah. So this is the parametric equation of a tangent plane. Okay, and you can also think about why it makes sense to have 2 variables. We have some plane, right? So imagine like T1 is, you have some plane, some level set, and T1 is some vector over here. It's tangent, meaning it's on my plane. I have some T2. And so like I need both of these things to represent my entire surface, my entire tangent space. Okay. Any questions on this problem? Okay, so I have a common problem here that I think is common listed here. It's a little bit similar to the previous question slightly, so I'm going to skip it for time and move on to linearization. Okay, so for linearization, there's lots of different types of problems. First type I've noticed is that you have some slope and you have a point, right? And you want to write the equation of, like you want to write some equation. For that, you can use point slope form. So point slope form is like y minus y naught equals some slope times x minus x naught. And this is usually used for if you're trying to approximate your function at a certain point. Then what you do is you take f at that original point. So I've added this f x naught y naught to both sides. And then I plus some change. So like this derivative times your x minus x naught stuff, that's like the change, like the error part of how you're estimating things. Okay, and the idea is that, say you're trying to estimate value at 2.2, 3.1. That's approximately equal to if you plug in your function at 2, 3, but there's a slight difference you're missing. And so that difference is this entire thing. That's your error, plus some like error difference. Okay, the other type of question is where they're asking you for, like, to actually find this error. Error is usually written as df. Df specifically is each of your partials multiplied by like dx, dy, dz. And you can almost think of this like implicit differentiation. Okay, and for your errors, there are 2 versions. So I have this little chart that you can follow. If they ask you for the amount of error, so like dv, oh, sorry, like if they say like the radius varies by 0.3, like they give you an actual number, that means they want you to find dv. So just d variable. But if they give you a percentage, that means they actually want you to find dv over v. So whenever there's a percentage, it's always this notation. You have d variable over variable. If they give you an actual number, they just want you to find d variable. Once you've determined which version they're asking for, you can see, are they asking for the absolute value version or the signed version? So if they tell you that some variable varies by 1%, then they're asking for the the percentage, and they don't specify the direction. So if they say like varies by 1%, it could be 1% greater, it could be 1% less. And so if they don't specify it, then they want you to do the absolute value version for this percentage. Now, if they're asking you for the numbers version, so like you're just finding d variable, then they could have two versions. If they say the radius is off by like positive 0.03, that means they actually want you to find a sign, like your final answer could be negative or positive. Again, if they just say like the upper bound for your thing, or like your radius is off by 0.3, like they don't specify any signs or anything, then they just want you to find the absolute value version, meaning you want to make your answer as large as possible. So like say in your actual like computation, you have 2, like dx or something is 2, and then dy turns out to be like -2. You don't do 2 minus 2 because that would not be maximizing our change. You want to do 2 plus 2 to give you 4. So like even if there's a minus sign here, if they're asking for the absolute value version, you just change it to positive because you're trying to like maximize your amount. Okay, so let's just do an example to see how this works. So let me do this example. So you want to consider a function. They say compute the differential. What is the differential? df. That's like your error. So df is going to be each of the partials dx plus the partial y dy plus the partial z dz. I can calculate my partial derivatives. So they wrote it out nicely for me, so I can just directly take the derivatives. Partial with respect to x is going to be 6x squared y squared over z dx. With respect to y is this thing, so this is a lot of partials, so I'm just going to write out the answer. You guys can check it later. So this is my differential. Now they say evaluate both f and df at 3, 9, and 2. So let's see. Wait, sorry. Wrong question. Partials are 8xy to -half c -2 dx minus 2x squared y -3/2 c -2 dy. Okay, this is very long, sorry. Okay, so this is my df. Part 2, evaluate f at those points. So I plug in 3, 9, 2 into my original function, and I can evaluate it to 3. I have my df. I can also evaluate it at those 3 points. And I'm going to get 2 dx minus a 6 dy minus 3 dz. Now they want me to approximate f at these 3 weird values, right? They're not very nice. So how do I do that? I'm first going to get my differentials. So whenever you see a D variable, that's like saying, what is the change in that variable? So in other words, dx is like change in x. And how am I going to get these changes? You can follow that. The differentials, so your D variable are always going to be your hard numbers minus your nice numbers. So here dx is going to be, what is the hard number we're trying to find? That's 3.1. The nice number is I can approximate it at 3. 3 is the closest like whole number I have to 3.1. I can do the same with y. Y, the hard number is 8.7. A number that's closer to it is 9. So I get -0.3. And dz is 2.2, but a closer number to it is 2. You get 0.2. And you see that these nice numbers that I chose are, they kind of hinted at those nice numbers in part B. Now that I have my differentials, let's do my formula. So f at the hard point, like the more difficult one, is going to be approximately equal to f at the nice point because it's about the same. But there's a slight like thing that's wrong. There's like a slight error. That error is df at the nice point. In other words, f at this weird 3.1, 8.7, 2.2 is approximately f at 392 plus df at 392. Okay. F392 I already found in part B. That was 3. Plus, what is df at 392? df was 2dx minus a 6dy minus 3dz. But I want to evaluate it at my nice point, which is the orange thing. What is missing? What are like these D variable things? Those are the differentials. And we just found the differentials up here. So now I can plug in my differentials. So I have 3 plus 2 times dx. Dx was 0.1, I found above, minus a 6. Let me write in orange, minus a 6. Dy is -0.3, minus 3, and dz is 0.2. And so my final answer is 3 minus 0.35, or 2.65. And so this is a very, I think, very common problem. Okay, any questions on that? Okay, almost there. Taylor series. So Taylor series, recall these like differential things. And the notation for this is that like these things in the exponent ABC, those are telling you that you want to take the partials with respect to A, B, and C, like whatever things they have here. And the order doesn't matter. Yeah. So for example, if they say I is 1, 0, 2, 1, what does that mean? You look at the corresponding numbers. So I should take the partial of X 1 time. I should take the partial of Y 0 times. You don't see anything there. I should take the partial of U 2 times. And I should take the partial of V 1 time. So D at this I value is going to be, you do all those partials with respect to V, order doesn't matter. So whichever one is easier to do first, you can do that. Okay, so that was the I notation. And remember, you can find like the order of I's. And I think there's like some other terminology for I. Don't quite remember. Okay. Then Taylor series, what are the ones to know? Just memorize these. You have sine, cosine, e to the x, natural log, 1 plus x, 1 over 1 minus x. These are the common ones I think we've seen. So yeah, just remember those. And we can manipulate Taylor series, right? So let's say we wanted to find the Taylor series of this thing. Then what do? I first look at the inside, cosine of xy minus yz. What is the actual Taylor series for cosine of any variable? Well, it's this orange thing. So what I want to do is I write x, y minus yz in there. And so everywhere I see a w, I want to write x, y minus yz instead. And I can keep doing that. What is natural log of, yeah, okay. So here we have natural log of a term, but we only know the Taylor series for natural log of 1 plus a term. So we're gonna have to do a little bit of adjusting. So why is that? Because we have this entire term. So imagine, yeah. So we have this entire term, but we need like 1 plus a number. So let's say that v is cosine of w minus 1. If v is cosine of this complicated thing minus 1, then plugging in natural log of 1 plus v will exactly give me what I want, cosine w. Right, and so natural log of cosine w, what is that? I can follow the natural log formula, which says it's v, in other words, cosine w minus 1, that's my v, minus the v squared, v is cosine w minus 1, over 2, plus dot dot dot. And now for each of the cosine w's, what were those? Those were the orange thing, cosine of the complicated thing. Cosine of w is 1 minus, like, this whole weird thing, plus dot dot dot, minus 1. So that's only the first term. Minus, you can do it again, plus dot dot dot. Okay, and depending on how high you want to go, you can put things in the trash can or simplify. Yeah, however you want. Okay. Let me go to final topic is critical points and optimization. So for critical points, where do critical points occur? They occur when your gradient is 0 or undefined. And from that, we can find the local extremum or the saddle points. So you have 2 tests. First derivative test just tells you if you take the gradient and set it equal to 0, those are your critical points. Second derivative test is you calculate the Hessian, and depending on the determinant of the Hessian, it's either extremum, and then you look at your trace. If trace is negative, you have a local max. If trace is positive, you have a local min. And if determinant is less than 0, you have a saddle. If determinant is 0, inconclusive. Okay. And you also have the Nash equilibrium. That was a little bit of the game theory stuff in one of the units. Okay, an actual last thing, constrained optimization, which is Lagrange. So we want to, if you're given some graph, you can find, yeah, sorry.
Will there be Nash equilibrium and game theory on the final? So I know we didn't, like the quiz didn't have any of that.
I think one of the quizzes may have had it. Did anyone have it on their quiz?
Well, that week it was like non-essential.
Okay, then maybe not. Yeah, I haven't seen the final, so I don't know for sure. Yeah. Okay, constrained optimization. From the graph, you can see what the max and mins are. So what you want to do is you have this constraint. Imagine you're walking on this constraint. You go from a lower level set to a higher level set and back down to a lower level set. So just from this picture, I already know this green point is going to be a maximum. Okay, and we know that this is some intuition on the Lagrange multipliers method. What is the point of Lagrange multipliers? It's so that you can find the absolute extrema. So let me do this final question from spring 2017 exam. So this is saying you have a factory full of robots that make pizzas. And X is greater, you have greater, like a positive number of robots. Each robot can be built to produce Y pizzas per hour. What is the total number of pizzas produced per hour? Okay, so what is the total number of pizzas produced per hour? You have X robots, each robot produces Y pizzas. So part one, pizzas produced per hour is X times Y. You have X robots, each robot can produce Y pizzas. So you have X times Y pizzas produced per hour. Question 2, assume the cost of a factory is this. For fixed production, so as soon as I see fixed, I know this is a constrained optimization problem because they're giving me some limits, some constraints. For fixed production, how should you allocate the number X and productivity Y of your pizza bots to minimize cost? So because it's a constrained optimization problem, I know to use Lagrange. What is my function? My function is 3x squared plus 6y. My constraint, they're saying I have a fixed production of 1,000 pizzas, meaning the number of pizzas I can produce per hour. What was the number of pizzas I can produce per hour? That was xy. They're saying that is 1,000 at most. So my constraint equation, if I move things onto one side, is xy minus 1,000. This is my constraint. This is my equation. I have my two things that I need. Lagrange multiplier says the gradient of C equals lambda gradient of my constraint. Gradient of C is 6x, 6 equals lambda. Gradient of G is yx. And so I follow the same method I always do for Lagrange. I write my equation I get from this gradient C equals lambda gradient G thing, which is the first row and the second row. And don't forget, my third equation is always whatever my constraint equation is, which is xy equals 1,000. So from Lagrange multipliers method, I have three equations. I can work with these and manipulate them. I can start with the first one, manipulate and get lambda is 6x over y. I plug this into my second equation. 6x over y times. Sorry, so I have, second equation, I have 6 equals lambda y. Let me solve for lambda. And I can set the lambdas equal to each other. So 6x over y equals 6 over x. I can solve 6x squared equals 6y, y equals x squared. Then I think I get stuck, but don't forget, I still have a third equation, the constraint equation. I can plug this in for y. So I get x cubed is 1,000 or x equals 10. If x equals 10, that means that from my xy equals 1,000 thing, y equals 100. So an x and y of 10 and 100 minimizes my cost. Okay, any questions on that?